The next standard thermodynamic process is an isobaric process. And as the name suggests, bar stands for pressure. Isobaric or isobaric also you can call it. It stands for a process which is carried out at constant pressure. Fine. Now, being an ideal gas, it must obey the ideal gas equation, the equation of state PV is equal to nRT. This time, pressure is being kept constant. So you put all the constants on one side, or you merge all the constants, you get volume is equal to nR by P. Okay, this whole thing becomes constant multiplied with temperature. Okay, therefore, it turns out that volume will be proportional to temperature if pressure is kept constant. Fine. This is called Charles's law. So when pressure of an ideal gas is constant, volume will be directly proportional to absolute temperature, temperature on the Kelvin scale. This is what is called Charles's law. Okay. So we know what happens in an isobaric process. Pressure stays constant. You increase temperature, volume increases. You decrease temperature, volume decreases. Right. So for this kind of a process, we should now draw the graphs, derive equations for delta Q, delta U, delta W, and then discuss molar specific heat, bulk modulus, how the process is carried out. Okay. So let's start with the graphs. First, PV graph. Now, what process is this? Isobaric process means pressure remains constant. If pressure remains constant, okay, and you are drawing the PV graph. Now, it's your choice. You can take pressure on y-axis or on x-axis. Let's say you take pressure on y-axis and volume on x-axis. Pressure is being kept constant. That means y-coordinate becomes constant. If y-coordinate is constant, the graph will be a straight line parallel to the x-axis. So volume may increase or decrease, but pressure stays constant. This is how the graph looks. Simple. So let's say this was carried out at a pressure P1. If you carry it out at a lower pressure, the graph will look like this. So it depends on how much pressure you are keeping the gas at while conducting or carrying out this process. This is how the PV graph will look. Simple. Next, pressure temperature graph. Again, pressure is kept constant, so pressure temperature graph also will look very similar. One of the coordinates is a constant, then only the other coordinate will vary. So depending on which axis you take pressure on, I'm taking pressure on y-axis, temperature on x-axis. So it's again like y-coordinate is constant. If y-coordinate is constant, the graph will be a straight line parallel to x-axis. So depending on what pressure you carry out the process at, you can draw the appropriate graph. The last one is the volume temperature graph. Now this is an isobaric process. Pressure remains constant, but volume temperature can change. And how do they change? We just discussed. Volume is nR by P multiplied with temperature. So volume is proportional to temperature. Now if y coordinate is proportional to x coordinate, the graph will be a straight line passing through the origin. Suppose you take volume on y-axis and temperature on x-axis. So the equation is of the form y is equal to some constant into x. Then that constant becomes the slope of the line. Okay, little bit of mathematics will be involved as I said. Y is equal to mx represents a straight line passing through the origin. Therefore, the volume temperature graph of an isobaric process will be represented by a straight line or will be a straight line passing through the origin. Suppose you take volume on the y-axis and temperature on the x-axis. You need to be careful with this. In the examination question, they may give you temperature on y-axis and volume on x-axis. Then the graph will slightly vary. It will still be a straight line passing through the origin, but the inclination will vary. The slope will change. Okay. Now, as I said, the graph is a straight line passing through origin. So it will look like this. We don't actually show it passing through the origin because volume cannot become zero. If volume becomes zero, that means there's no gas at all. So don't make the graph actually pass through the origin. We show a dotted line. Okay. Let's say at particular pressure P1, you get a graph like this. Now the same gas, same system, if its pressure is kept something else and the process is carried out, then the slope of the graph will vary. Why? Because the equation we have, the governing equation for this graph is V is nR by P multiplied with T. This is the slope, right? So depending on the pressure, if you keep the number of moles same, okay, as I said, it's the same gas. Depending on the pressure, the slope will change. And see, we took volume on the y-axis, temperature on the x-axis, no? So the proportionality constant between them will automatically be the slope. So slope of this graph is nR by P. That means if pressure increases, okay, not during the process. During the process, you can't change the pressure. It's an isobaric process. Okay. So if you carry out the process once again at a higher pressure, what happens is if pressure increases, the slope decreases. So slope decreasing means what? It will be more parallel to the x-axis. I mean, it will tend to become parallel to the x-axis. So from these two graphs, we can say that P2 is greater than P1. We increase the pressure at which the process is carried out. The graph will become or will tilt more towards the x-axis. Slope decreases. So lower pressure, higher slope. Higher pressure, lower slope. Okay. But this is because we took volume on the y-axis, temperature on the x-axis. If you take temperature on y-axis and volume on x-axis, then it will get reversed. Okay. Fine. So these are the process graphs for an isobaric process. PV graph, pressure remains constant, volume changes. It could increase, it could decrease depending on what you are doing with the gas. Pressure temperature graph, pressure remains constant, temperature could increase or decrease. Volume temperature, both change and they change proportional to each other. So the graph will be a straight line passing through the origin. Okay. The next thing we need to know is how to calculate delta U, delta W and delta Q in this kind of a process. We'll start with delta U. Change in internal energy in an isobaric process. Okay, at least now one of you quickly tell me what is the basic formula for delta U from what we learned in Maxwell's law. Quick, I want answers, only then we can proceed. I got one answer as F by 2 nRT. See, U is F by 2 nRT. If you want to know how much is the internal energy of a gas, you use this formula. We are interested in change in internal energy. You should write F by 2 nR delta T. Okay. So, see, you can use this formula directly if the type of gas is given. Based on type of gas, monatomic, diatomic, polyatomic, you can tell number of degrees of freedom. Then number of moles should be given and the temperature change should be given. From what temperature to what temperature the gas is being taken. If you know those, you can use this formula directly. But many times in thermodynamics, the question will be given or the information will be given in terms of pressure and volume also, not just in terms of temperature. Pressure, volume, temperature are related through ideal gas equation. PV is equal to nRT. Okay. If the left hand side changes, the right hand side changes. But left hand side, right hand side should always be equal. What does that mean? Generally, change on the left hand side will be equal to change on the right hand side. Okay. Fine. Right hand side is nRT. So change in PV will be equal to change in nRT. What does that mean? P final V final minus P initial V initial will be N and R are constants anyway, or you can write nR T final minus nR T initial. This can be done for any process. You can write it this way. Change in left hand side of the ideal gas equation is equal to change in right hand side. See, these are some of the mathematical techniques that you can use while solving problems. Okay. Now, what kind of process are we talking about? Isobaric process means pressure remains constant. Pressure constant means what? P2 is same as P1. You can call it as P. Then, if you take P common on the left hand side, you will be left with V2 minus V1. And on the right hand side, you can take nR common. You will be left with T final minus T initial. Therefore, now see, here I'll have to put a star because this is valid. This step is valid only for isobaric process. Pressure has to be constant. Therefore, you can write pressure into change in volume is nR into change in temperature. So nR delta T can be replaced with P delta V. And if you do that here, you can write it as F by 2 into P delta V as well. So if you know pressure and volume, using that also you can tell what is the change in internal energy of the gas. Okay. Now F by 2 nR delta T is generally valid. F by 2 P delta V is valid only when the process is isobaric. Okay. These derivations, if you do once on your own, no, they'll be more, it'll be easier for you to memorize. Okay. And it'll be more comfortable for you to apply. So anyway, this is how we calculate change in internal energy of a gas during an isobaric process. So just like how we did for isothermal, we use the basic formula and apply it to this particular process. In isothermal, it turned out to be zero because temperature doesn't change. In isobaric, this is how you calculate change in internal energy of the gas. Okay. Next is work done by the gas in an isobaric process. And again, quickly, what is the basic formula for work done by a gas? Okay, I got one answer as work done basically is P delta V. See, generally work done is not P delta V. That is wrong. Okay, many students have this misconception. It is P delta V is not work done. Work done generally is integral P dV. Okay. Now, what kind of process are we talking about? Isobaric process. In an isobaric process, pressure is constant, so you can put it outside the integral. Then it changes to P integral dV. So this step is valid only for isobaric process. This is the general formula. Okay, I asked for the general formula. Fine. So constant pressure multiplied with integral dV. dV stands for small change in volume. Integral dV becomes total change in volume. Therefore, work done in an isobaric process can be calculated like this. Pressure multiplied with the volume change that happens. And we just proved that for an isobaric process, okay, P delta V can be written as nR delta T. So you can do the same here. You can write it as nR delta T as well. You can calculate work done in an isobaric process this way also. So P delta V or nR delta T, any one of them can be used. So if pressure and volumes are given in the question, you'll use P delta V. If temperature changes are given in the question, you'll use nR delta T. So it depends on the question, which approach you take. Okay. Now we have a formula for delta U, change in internal energy. We have a formula for delta W. Then you can easily express delta Q in an isobaric process. How? Delta Q is delta U plus delta W. We got delta U. Generally, delta U is F by 2 nR delta T, right? And delta W, we just proved that it can be calculated as nR delta T in an isobaric process. So all this is valid for isobaric. Okay. Putting these two together, adding these two, it becomes F by 2 plus 1 multiplied with nR delta T. So you can calculate it this way if required. Okay. Done. So We derived formulas for delta W, delta U, and delta Q in this kind of a process. Next thing we need to derive is the molar specific heat. Basic formula for molar specific heat, delta Q divided by N delta T. Now we just derived that for an isobaric process, delta Q is F by 2 plus 1 multiplied with NR delta T. Now send N and delta T to that side. Denominator on the other side. So you get delta Q by N delta T as what remains? F by 2 plus 1 multiplied with R. Then that itself should be the molar specific heat for this kind of a process. Now, what kind of process is this? Isobaric process. So we call this as molar specific heat at constant pressure for a gas. It is denoted by the symbol Cp. You can write Cp is equal to F by 2 plus 1 multiplied with R. It depends on the degrees of freedom, means it depends on the type of gas. So for monoatomic, Cp, for monoatomic, degrees of freedom are 3. 3 by 2 plus 1, it becomes 5 by 2 into R. Okay. For a diatomic gas, diatomic has how many degrees of freedom? 5 degrees of freedom. Then 5 by 2 plus 1 becomes 7 by 2 multiplied with R. R is the universal gas constant. And polyatomic nonlinear. Polyatomic nonlinear has 6 degrees of freedom. 6 by 2 is 3, 3 plus 1 is 4. Cp will be 4R. So molar specific heat of a process carried out at constant pressure varies from gas to gas. Okay, interesting questions can be asked based on this also. They can give you a mixture of gases and ask you what is the effective molar specific heat. Okay, they can, yeah, fine. Yeah, that's what they can ask. So molar specific heat part is done. Next is bulk modulus. Let us quickly discuss that also. Bulk modulus of an ideal gas undergoing isobaric process. Bulk modulus generally by definition is minus V dP by dV. Now, in an isobaric process, pressure does not change. If pressure does not change, change in pressure will be zero. Volume changes. Okay, temperature and volume will change, but pressure won't change. So if that is zero, the bulk modulus is zero. Okay, in an isobaric process. What does bulk modulus being zero mean? I just told you when we discussed the previous process that bulk modulus shows you how elastic the system is. Elastic means how difficult it is to compress. Okay. If bulk modulus is zero, that means there is zero difficulty to compress, free compression. Okay. That is what it means. Okay. So basically, as you compress the gas, its pressure is not changing. Means it does not give you any extra resistance to compression. So you can compress it at the same pressure. That is what happens in an isobaric process. Now, you may say that, sir, if we are compressing something, pressure must increase. You are changing temperature accordingly such that its pressure does not increase. Fine. Now, here we can give an explanation based on kinetic interpretation of pressure. We had derived that PV is equal to 1 by 3 mn average of square of speed of the gas molecules. Right? And from this itself, we got PV is equal to nRT. So, we are compressing the gas, means we are decreasing its volume. Accordingly, if the speed of the gas molecules decreases, then it's possible for pressure to remain constant. Speed of gas molecules decreasing means what? Kinetic energy of gas molecules decreasing. That means temperature decreasing. Okay. So if volume temperature decrease proportionally, pressure can remain constant. That is what happens in an isobaric process. Okay. How an isobaric process is carried out and problems based on it we'll do in tomorrow's class. And we'll also discuss some more thermodynamic processes. Okay. Thank you all. We'll continue tomorrow.